Möbius band and the cylinder can both be made from flat rectangular strips by gluing together the opposite edges, but the direction of gluing is different. For the cylinder, you just glue the edges together without twisting them, whereas for Möbius band, you have to give a half twist before gluing. Well, in fact, there's no homeomorphism between the Möbius band and the cylinder, and one way of proving that is to count the number of boundary curves. The cylinder clearly has 2 boundary curves, whereas the Möbius band only has 1. Think of this point here and follow round the boundary with your eye. You eventually get back to this point, having traversed the entire boundary curve exactly once. Well, the number of boundary curves is a topological invariant, and that proves there can't be a homeomorphism between the cylinder and the Möbius band, because the cylinder has 2 boundary curves, whereas the Möbius band only has 1.
Actually, there's a more interesting topological property which also distinguishes the Möbius band from the cylinder. It's the one we're going to investigate for the rest of this program, orientability, and the cylinder has it, whereas the Möbius band does not. Take a pair of vectors in the surface of a cylinder and send them on a journey all the way round. When they get back to where they started, they'll point in their original directions, except perhaps for a rotation. This may seem rather obvious, but in fact it doesn't happen on the Möbius band. When the vectors get back, they're upside down. And no matter how you rotate them, you can't put them into their original directions. Now that's very strange, because if you imagine the vectors as being the hands of a clock, what happens to the sense of clockwise if the clock travels round? What goes out as clockwise comes back as anti-clockwise. Watch it again. So, on the Möbius band, there's no coherent sense of clockwise. And that's what we mean by non-orientable. No coherent sense of clockwise. In other words, although close neighbours might agree on what clockwise is, you can go on a journey and return with that sense of clockwise reversed. Of course, you could choose to start out with the sense of anti-clockwise. The question is whether the sense you've chosen gets reversed. And for the Möbius band, it does. Well, that's a very peculiar property, and it's not surprising that orientability is a topological invariant. Let me show you another non-orientable surface. Take 2 Möbius bands and cut a disk out of each. Then, glue the edges of the disks together by extending them like this and gluing, and you get this surface. It's topologically distinct from the Möbius band. For a start, it has 2 boundary components instead of 1, but it's still non-orientable. Because if you took a clock here and went round, all the way round and round the bottom and up, back to here again, you'd still have gone round a Möbius band, and the clock would come back reversed. That's true for any surface which contains a Möbius band, so such a surface can't have a coherent sense of clockwise defined on it, and it's non-orientable. Let's get back to orientable surfaces, surfaces which can be given a coherent sense of clockwise. A surface is called orientable if we can assign a sense of clockwise around each point which is matched by a travelling clock, no matter what journey it takes. We can do that on the cylinder. So it's orientable, although we haven't actually proved that yet, because we took our clock on only one journey. It has to match up after every conceivable journey. The sphere also seems to be orientable on intuitive grounds. We have a clear sense of clockwise everywhere on the surface of the Earth. But again, that's not a proof. We can get a clue as to how to check orientability for a general surface by looking at the simplest orientable surface, the disk.
The orientability of the disk is intuitively obvious. In fact, our intuition is matched by a very simple proof. Just choose a direction of travel round the boundary and call that clockwise. That supplies a coherent sense of clockwise to every point, because you can just shrink this boundary circle onto any one of those little circles. And whatever journey you choose, you can use these little clocks to transport your sense of clockwise around. So your sense will obviously come back the same. Now, this method of orienting the disk can be adapted to give us a rule for deciding whether a general surface is orientable. Remember that our definition of a surface is that it's made of little patches or disks. So instead of trying to orient each point of a surface, we could orient patches of it in the same way that I've just described for the disk, namely by choosing a direction of travel round the boundary of each patch. And then we'll need to check whether this process does indeed give a coherent sense of clockwise on the whole surface. Actually, it's convenient to carry out the process using triangular patches, because we know we can subdivide every surface into triangles. Now, what's involved in having a coherent orientation on the whole surface? For example, what happens when we have two neighbouring triangles, each with the same orientation? What happens at the common edge? Well, on this triangle, clockwise is given by these directions on the edges. So the common edge gets directed oppositely in a neighbouring triangle. For a coherent orientation on the whole surface, this has to happen on every common edge. Conversely, if the surface is non-orientable, you won't be able to find a coherent way of orienting all the triangles. Whatever you do, you'll always end up with a common edge which is not directed oppositely. So there's our rule for orientability. Orient triangular patches and check all common edges. And the same rule applies if your surface is represented as a polygon divided into triangles with some pairs of edges identified. But you have to be careful on those identified edges. For example, here's the cylinder represented as a polygon made up of two triangles. And here's what appears to be a coherent orientation. Let's check that it satisfies our rule for common edges. It's okay on the diagonal. That's directed oppositely in the two triangles. But what about the other common edge, which consists of this identified pair? Well, the orientation direction is opposite the identification arrow here, and it coincides here. So when we glue the edges, we're bound to find that the rule is satisfied. Upwards in this triangle, and downwards here. So this is a coherent orientation on the cylinder. We've proved that the cylinder is orientable. For the Möbius band, we should find that this doesn't work, because we know it's non-orientable. So let's try. We've subdivided the Möbius band into 8 triangles. And because we chose to orient the first one clockwise, we were forced to put a clockwise orientation on all the other triangles, including the last one, in order to get the interior edges directed oppositely. But now, on these two edges, the relationship between the orientation arrow and the identification arrow is the same in both triangles. Actually, they coincide, but if we'd used the opposite direction for the identification arrow, they would have disagreed in both. But that means that when we glue up the Möbius band, we're going to get a mismatch. The common edge is directed upwards in both triangles. And we've now got an orientation change here, clockwise here and anti-clockwise there.
Of course, for a complicated surface, whether it's glued up or not, the procedure of orienting triangles and checking common edges could be extremely tedious. But in fact, we don't have to apply the method directly. Instead, we can use it to prove a theorem, which makes things much easier. Half the theorem is actually trivial, and I've already mentioned it. If a surface contains a Möbius band, it must be non-orientable, because you can send the clock round and get it back reversed. Well, that's half the theorem, but we can actually prove that the converse is also true. If a surface is non-orientable, then it contains a Möbius band. And this full theorem is a simple criterion for orientability. The non-orientable surfaces are precisely those which contain a Möbius band. But we still have to prove this part of the theorem.
Suppose you have a non-orientable surface which you've subdivided into triangles, and you start orienting each triangle in turn. That is, you orient one triangle, then you go on to an adjacent triangle and orient that consistently with your first triangle, and so on. Eventually you must get a mismatch because the surface is non-orientable. If you stop orienting at that first mismatch, your root of oriented triangles will look something like this. Here's the first triangle, oriented clockwise. Here's the next, and the next, and the next, and so on. And the root might intersect itself like this. In fact, there might be several intersections. And eventually, there'll be a self-intersection which gives the mismatch. Here, you went out clockwise, and you've come back anti-clockwise. Well, there's a Möbius band in this root. To find it, you just discard irrelevant loops like this, and you discard the first few triangles, and you're left with a simple loop of triangles which contains a mismatch. Now, this loop may not itself be a Möbius band, but it will certainly contain one. We can see that if we cut the loop here and consider a flat representation of it. Assume it has 4 triangles for simplicity. And here's the pair of identified edges. We know they must be identified in the opposite directions, like this, because that's the only way the clockwise orientation could fail to direct this common edge oppositely. Well, this looks like the Möbius band we're after, but in fact it may not be a Möbius band because the top and bottom edges may be identified in some way. We may have unglued some edges when we flattened it out. Nevertheless, it contains a Möbius band. A band like this, cut out of the middle, is a Möbius band because it has just one pair of identified edges, and they're identified in opposite directions. And that completes our criterion for orientability. We've proved that every non-orientable surface must contain a Möbius band. Therefore, any surface which doesn't contain one is orientable.
Well, that brings us to the final section of the program, in which we'll discuss a very intriguing result about non-orientable surfaces. That some of them just can't be embedded in 3 space. That is, they can't be constructed physically in 3 dimensions. We've seen 2 so far which manifestly are embedded in 3 space. The Möbius band and the Möbius band joined like this to another Möbius band. Actually, we've seen a third one. the Möbius band with a disk cut out of it, because we made this one by gluing together two copies of this. And we could repeat this process to join a third Möbius band to a double one, just glue the boundary of this hole to a hole cut out of the double band. Each time we add a Möbius band, we get a new topological surface, which we know is non-orientable because it contains a Möbius band. It's new because we increase the number of boundary components by one each time. But what about a non-orientable surface without boundary component? Well, all the ideas we need to construct one are already here. We know we have to join a Möbius band to something, and we know we have to glue boundaries together. So instead of cutting a hole first to make a new boundary, why not try gluing the existing boundary to something?
In fact, why not glue two intact Möbius bands along their boundaries? That'll get rid of the boundary components. We've coloured each boundary in two halves, red and white, to show you how the boundaries might be glued, with the colours matching. Difficult to see how it can be done, and it's difficult even if we look at the flat rectangular representations. Let's be quite clear what a boundary component is. If we start here on the band, which is this point on the rectangle, and follow along the red, when we get to this point here, we have to jump down to here on the rectangle, and then follow around the white back to this point again. So the boundary is E followed by F. And we have to glue that to the C followed by B boundary. In other words, we have to glue C to E and B to F. Well, we can actually perform the gluing of C to E by putting the rectangles close together like that. And then we have to glue B to F, and let's call them X. And let's distort the rectangle into a hexagon to make it more symmetrical. So here are B and F, now called X, and here are the two A's, and these two white arrows are in place of the two D's. What I'm going to do is to cut the hexagon along this line here. And I put a red arrow on to remind me where I'm going to make the cut. So here's the hexagon in two pieces, and in order to glue the two white arrows together, I'm going to have to turn the triangle upside down. So I've joined the white edges together, but I've created a new pair of identified edges, the red arrowed pairs. So the final step, we're going to distort this into a rectangle. That is, we're going to bend the two A edges up so that they follow on from the X edge. I don't need to remember the white arrowed edge anymore because I've glued that pair, but the red arrows are important. They have to be glued, and they have to be glued in opposite directions. And I've got to glue the top and bottom edge in the same direction. Well, we've arrived at a nice representation for our non-orientable surface without boundary, and it's actually called a Klein bottle. Let's try and make a model of it in 3 space. Let's glue the top and bottom edges first. To glue the left and right edges, let's try bending them towards each other like this. So this doesn't work. The identification directions don't coincide. Let's try curling the ends inwards. So this doesn't work either. Finally, let's leave the left-hand end inside, but pull the other end outside. And now the identification arrows do match, but we can't glue the edges without making the surface intersect itself. So we don't get an embedded surface. Let's be clear about the problem. Our construction gives a perfectly good surface. A polygon with identified edges like this is locally disk-like, which is our definition of a surface. And the surface is non-orientable because it contains a Möbius band. We made it from 2 Möbius bands. And it has no boundary components because edges are identified in pairs. So intrinsically, we've got what we wanted, a non-orientable surface without boundary. But we can't embed it in 3-space. If we try to make a model of it, and here's one like the one you just saw, then identifying the edges correctly forces a self-intersection. That is, it forces us to identify a circle on this tube here with a circle on this tube here. And that identification isn't part of the gluing recipe. So this is not an embedding of the surface we started with.
Well, you might say that was just one try at an embedding. We perhaps could have a different go and succeed. However, it turns out that the only surfaces without boundary which can be embedded are the orientable surfaces. And we'll end the program with a brief indication of why that's so. Consider a general surface without boundary. The first result we need is that if the surface is embedded in 3-space, then it must have an inside and an outside. That is, it must divide R3 into precisely 2 regions, outside and inside. Well, we're not going to give a rigorous proof of that, but you can see why it's true. Any region of space I can actually get at without touching the surface is the outside. When I touch the surface, I'm on it, and the inside is all the points I have to cross the surface to get at. Now, having an outside and an inside means a surface must be orientable, because we can orient it as follows. At each point of the surface, define an orientation as a right-handed screw inwards. Do that at each point and you get a coherent clockwise. Why is that? Well, the right-hand screw rule can be made precise like this. Make a set of 3 axes with your right hand and point inwards with your index finger. Then the clockwise orientation is the direction from your second finger round to your thumb. Now, if you go on a journey round the surface, your sense of inwards can't change unless you go out with your right hand and come back with your left, which would make the whole of 3-space non-orientable. And that does it. A surface without boundary embedded in 3-space must be orientable. So no non-orientable surface without boundary can be embedded.